very much to the organizers for having me. I'm wearing this cool microphone. If I knew I was going to have a microphone like this, I would have worked some cartwheels or breakdancing or something into my talk. But unfortunately, it's going to be quite a lot more boring than that. Is this how I advance slides? Okay. So no doubt, there we go. So no doubt everyone in the room is aware that in recent years, a debate has taken shape about whether new tools of human genome editing ought to be used to make heritable modifications to the human genome. And surely you're also aware that this has in fact already happened. Last November, it was revealed that a scientist in China had modified the genomes of 2 embryos in an attempt to make them immune to HIV, and that those embryos grew into twin girls who were born late last fall. So the lives of these twins from their very inception have been shaped by a scientific desire to author human futures. It's an understatement to say that emerging capacities of this sort at the nexus of developmental biology, biotechnology, and reproductive medicine present truly unprecedented bioethical challenges. This is so not merely because of where these technologies might take us, but because of where they've come from. They're unfolding within a technological, medical, and importantly, a social context that's been long in the making. The last 40 years of reproductive technology on the one hand, and molecular biology on the other, has produced a powerful infrastructure for integrating human genome editing into human reproduction, for authoring human lives and futures in an unprecedented manner. That infrastructure is technological and biomedical, but it's also political and ethical. One of the most important factors that will shape the future of this technology, I want to argue, is the way our society tends to imagine, deliberate, and govern developments in biotechnology. And that's what I want to make the focus of my talk tonight. Modes of deliberation and governance shape what questions are asked and what questions go unasked, what perspectives are privileged or silenced in public debate, and what priorities and practices come to be embedded in our institutions. I want to draw attention to how we tend to distinguish between scientific issues and ethical issues, and as a corollary, how we distinguish between those who know best in a scientific sense and those who know best in a moral sense. The ways societies judge who knows best and delegate responsibilities to them to make decisions is of enormous consequence, not just to the place of science in shaping social life, but I want to argue to democracy itself. It shapes how we deliberate about the meaning of advances in the biosciences and biomedicine, in what terms, through what institutions, and at what stages of scientific and technological development. Governing the future well requires that we understand the trajectory that we're on and what tacit commitments have shaped it. So the debate about human gene editing was touched off in early 2015 when a Chinese group applied CRISPR to human embryos. This catalyzed an effort by the US National Academies, together with the Royal Society and the Chinese Academy of Sciences, to convene an international summit on human gene editing, the first of 2, which took place in December 2015 in Washington, D.C. This is Nobel laureate and former Caltech president David Baltimore opening the summit. He opened it by explaining why it's urgent to address the implications of human genome editing. Although genetic engineering techniques have been around for decades, he explained they were imperfect, and applying them to human beings was therefore initially unthinkable. But with technological advances, the, quote, unthinkable has become conceivable. Thus, now we must face the questions that arise. How, if at all, do we as a society want to use this capability? So let me point out that this narrative follows a familiar sequence. Scientific knowledge generates technological applications, which in turn produce societal impacts and consequences, from science to technology to society. This is the linear model of innovation, an idea that has underwritten public investment in science in this country since World War II. The linear model is as old as post-war public science and is the dominant paradigm for biomedical research as well. Think of the structure of NIH. Its proof of principle was the fact that public investment could, in the space of just a few years, go from equations and chalkboards to this. Again, the trajectory is linear, from theoretical physics to the bomb to its social consequences. Now, there are many reasons to question the linear model. Science and technology are profoundly shaped by societal priorities and desires, by capital and markets, and by legal and political arrangements. But my question is not so much whether the linear model is a true representation of innovation, but instead I want to focus on how the assumption that it is shapes ethical deliberation and governance. This is J. Robert Oppenheimer, as it were, the father of the bomb. Quote, "In some sort of crude sense, which no vulgarity, no humor, no overstatement can quite extinguish, the physicists have known sin, and this is a knowledge which they cannot lose." This famous quotation is variously invoked as marking physics' loss of innocence, as acknowledging its Faustian bargain with the military-industrial complex, or simply as reflecting a kind of unforgivable naivete of the scientists whose heedless curiosity inaugurated the nuclear era. But I want to note something else about it. Married to this acknowledgement of culpability is a declaration of power. It is we physicists who created this world. It was conceived in our minds, wrought by our hands, and is a product of our choices and will. Thus, it is we who bear responsibility. This is a linear model of scientific responsibility. Science produces the technological future and its corollary social transformations. Scientists' choices seal society's fate. This account of scientific responsibility was formative for the development of molecular biology. Numerous physicists who were involved in the Manhattan Project defected to biology after World War II in search of redemption. They were central to the development of molecular biology in particular, both in its technical achievements but also in its ethos. This new biology, as they saw it, would serve life rather than death, healing rather than harming society. The shadow of sin would not be cast over the light of the life sciences. But note once again that this declaration of responsibility, or this ethos of responsibility, was also a declaration of power. The power to produce the knowledge, to produce the technologies that will fundamentally alter life, and thus also the power to choose between healing and harming. We tend to think of this in the morally neutral terms of expertise. Those who create the technological future are also in the best position to foresee and guide it. This idea of expertise empowers scientific experts to declare, in Baltimore's terms, when the unthinkable has become conceivable, and therefore also when we must face the questions that arise. How do we want to use this capability? So I want to point to a consequential slippage here. It's a slippage between the first and the second we. The we of we must face the questions that arise, and the we of we as a society. Here's what Baltimore said next. "We are taking on a heavy responsibility for our society because we understand that we could be on the cusp of a new era of human history. The actions that we take now will guide us into the future. We are initiating a process of taking responsibility for technology with far-reaching implications." We are taking responsibility for our society because we understand the actions that we take now will shape the future. So I want to ask, who is this we, and what authorizes this we to take responsibility? This idea of taking responsibility and of the we who takes it is consequential for three reasons. First, because it configures the politics of how we evaluate and govern emerging technologies, including those that touch upon fundamental dimensions of human life. It shapes who's there at the table, what gets taken into consideration, and even the very terms of debate. Second, because it shapes the technological future. That is, it shapes scientific practices, and therefore technological trajectories, and social, legal, and moral environments. These environments are not incidental to what technologies come into being. For instance, if deliberation and governance focuses on the products of biotechnology rather than the processes and scientific priorities that produce them, we end up with a very different world. A focus on the product tends not to ask, what trajectory is this research putting us on, and is it a good one? But rather, it asks, what are the risks and benefits of this particular technology? Note that focusing on the product comports with a linear model. Law and ethics step in at that moment of transition from technology to society. Society does not, and on this account ought not, interfere with so-called basic science, because if society meddles, it might miss out on future technological benefits. It's the wrong phase to ask the question. This linear model of responsibility is in this sense most fundamentally a model of governance. Scientific practices and priorities remain the province of that we who takes responsibility for our society to the exclusion of the rest of us. Third, This idea of the we that takes responsibility subtly shapes the contours of collective moral imagination. This is the most important point. The linear model delegates to experts the authority to imagine the future, to declare what is or isn't coming, and thus what warrants worry, what technological futures are possible, desirable, and good. So by authorizing experts to imagine the future, we simultaneously authorize them to delimit the parameters of moral deliberation. That is, we authorize them to mark certain scenarios as unrealistic and therefore not worth talking about, and thus to exclude their moral corollaries. Put simply, the notion is that scientific judgment precedes and must precede ethical deliberation. Science first, ethics second. This idea has profound consequences for what sorts of ethical debate takes place and under what circumstances. In this approach, debate about human germline genetic engineering and about the moral commitments and judgments about it must wait until a David Baltimore declares that the unthinkable has become conceivable, and now we must decide what is to be done. But let us note that the question of whether it's right and appropriate to modify our children's genomes transcends the technology of the day. It touches upon long-standing questions about what dimensions of human life ought not be taken as objects of manipulation and control. And those questions are not new. Indeed, they were already a focus of significant debate more than half a century ago. Some of the most prominent biologists of the mid-20th century were leading figures in these discussions. These discussions focused not on specific technologies, but on the general potential to author human futures. And they were, in some cases, unabashedly ambitious in their vision of the perfectibility of the human. So for instance, Robert Sinsheimer, a highly respected molecular biologist who died only relatively recently, and whose research was foundational for the development of biotechnology, who was the president or chancellor of University of California, Santa Cruz for a while. In 1979 celebrated, quote, defined genetic improvement of man as a means to, quote, carry on and consciously perfect the human species. This was a kind of a common sensibility. And the ethical questions they raised were equally ambitious. In 1962, Julian Huxley, maybe the most important evolutionary biologist of the 20th century, envisioned powers for directed human evolution that raise, and he thought must be guided by, what is of course a quite profound question: what are people for? Yet even as technology advanced, debate narrowed. The first baby was born through IVF in 1978. The first successful germline alterations of mice took place around 1980 and elicited widespread concerns that human embryos, now accessible to laboratory manipulation through IVF, might too become subjects of genetic manipulation. In a letter to the Carter administration, 3 major religious organizations in 1980 called for greater attention to the, quote, new era of fundamental danger triggered by the rapid growth of genetic engineering, and to associated questions of the fundamental nature of human life and the dignity and worth of the individual human being. In response, a federal bioethics body conducted a study of human genetic engineering, this is in 1981, 1982, called Splicing Life. Splicing Life marked a kind of important moment of transition in these discussions. It eschewed the wide scope of earlier ethical debate for a more narrow approach, one that should be more familiar to us now, that was taking shape with the emergence of professional bioethics. One of the central questions that it asked was how society ought to go about asking ethical questions about these sorts of technologies. Note that the Beecham and Childress Principles of Biomedical Ethics is just a couple of years before this. A couple of years before this is also the development of the Belmont Principles. There's sort of the discourse of bioethics is taking shape, and it's delimiting the kinds of questions that are deemed appropriate to ethical deliberation, at least sort of public ethical deliberation. So in particular, the Splicing Life report set its sights on talk of, quote, playing God. The commission argued that reasoned public deliberation requires shared secular terms of debate that everyone can engage with. This required translating playing God, they thought, into secular terms, so they undertook a kind of interpretive project. In doing this, the commission made 2 moves. First, it suggested that the, quote, rational kernel of the notion of playing God is, quote, avoiding negative consequences. So a technological capacity like human genetic engineering is not wrong as such. It can't be unethical as such, but only insofar as it has bad consequences. In short, the technology is morally neutral. Only its uses can be good or bad. Note, by the way, that this suggests that legitimate ethical questions kick in only after a technology exists, at that moment of transition into society, not in the making of it, but in its use. Consequences of use don't leave space, therefore, for asking questions about what aspirations gave rise to it, and in a sense are built into it, and whether those aspirations are virtuous. The second thing the Commission did was to suggest that there was no need to engage with ethical questions for scenarios that are technically implausible or very risky. So, while some imaginable scenarios may raise real ethical questions, because those uses of genetic engineering are still in the realm of science fiction, they need not and ought not be discussed. Or alternatively, because they're so risky, that in a sense settles the ethical questions before you ask any more complex ones. It's just unsafe. So by focusing on consequences and giving technical experts a kind of a monopoly on deciding what technological futures and what consequences are plausible, the report rendered questions of, quote, the fundamental nature of human life and the dignity and worth of the individual human being out of bounds for purposes of public ethical deliberation and governance. It was irrelevant. If human genetic engineering is just too risky to do on simple grounds of safety, there was no reason to get into more complex questions of human integrity or dignity or the like. Just a little historical aside, it's worth noting that the notion of controlling human reproduction as playing God came not from unschooled religious naysayers, as the Splicing Life report sort of made it out to be, but rather from a secular source, from the highly respected scientists who were celebrating the new scientific capacities that I spoke about a moment ago. So this is Julian Huxley, again commenting on how, because with advances in evolutionary biology, we now know where we have come from, we are thrown into a position of becoming responsible for humanity's evolutionary future. Quote, evolutionary man can no longer take refuge from this loneliness by creeping for shelter into the arms of a divinized father figure whom he has himself created, nor escape from the responsibility of making decisions by sheltering under the umbrella of divine authority, nor absolve himself of the hard task of meeting his present problems and planning his future by relying on the will of an omniscient but unfortunately inscrutable providence. No, those responsibilities fall to us. We can, should, and therefore must play God. This is, he thought, an unavoidable responsibility, and one that requires us to think about what forms of ultimate human purpose should guide our scientific and technological projects. So, playing God, both the phrase and, you might say, the aspiration, originate sort of at the very inception of modern biology itself. But that's just an aside. So, Splicing Life supplied a rationale for narrowing the scope of debate, and policymakers followed its advice. From 1983, the federal body that oversees genetic engineering research, the Recombinant DNA Advisory Committee, declared that we will not at present entertain proposals for germline alterations. This policy remains in force decades later. The relatively narrow focus on issues of feasibility and risk became the focus of the RAC, and persisted even as gene therapy became a major focus of ethical debate in the 1990s. The RAC continued to see germline gene therapy as unrealistic because technically infeasible and risky, and therefore, in effect, not worth talking about, and therefore the prohibition stood. This approach continued to discourage engagement with the broad ethical questions of pre-1980s debate. As a body that was initially made up of only scientists, it's perhaps not surprising that it focused narrowly on technical risk to the neglect of other ethical dimensions. But this focus proved consequential, not least because this was the authoritative body that had a kind of a monopoly on these questions. It's worth also noting as an aside that the same historical developments gave rise to a very different conversation in Europe, leading ultimately to the Oviedo Convention, the Convention on Human Rights and Biomedicine, which includes as one of its articles a categorical prohibition against heritable human genetic modification. So they're sort of different trajectories. So the RAC's job was to implement guidelines for recombinant DNA research that were developed in the mid-1970s at the famous 1975 Asilomar Conference. So in the early 1970s, a group of prominent scientists called for a voluntary moratorium on recombinant DNA techniques out of concern that they might unwittingly create dangerous new pathogens. It was a sort of transition from descriptive biology into producing new life forms. In 1975, they convened a meeting at the Asilomar Conference Center in California to assess the risks and establish guidelines for research, guidelines that they hoped would simultaneously limit biohazard risks and forestall public regulation. It was an extremely consequential moment for the development of biotechnology, but also for the sort of associated ideas of scientific responsibility and modes of scientific self-regulation. Most of the participants were biologists. This is David Baltimore. There were also a few lawyers and a handful of members of the press. So the meeting is remembered as a sort of defining act of scientific responsibility, doing in biology what the physicists had failed to do with the bomb. But it was simultaneously an expression of control, of the power to know, shape, and govern the biotechnological future on behalf of the rest of us. One of the most important dimensions of the Asilomar meeting is what went undiscussed. So David Baltimore also opened this meeting in 1975, and he declared two topics out of bounds: bioweapons, or the biosecurity implications of recombinant DNA, something that is coming back to bite us now, and its social and ethical implications. He called the former a problem for the national security apparatus, and the latter of irresolvable private moral and religious beliefs. Thus, how these technologies might be used and what their uses might mean for wider society was explicitly taken off the table at Asilomar. Instead, it focused narrowly on technical risk assessment. That technical framing was used to justify not only the recommendations that came out of the meeting, but the lack of public participation in formulating them. If risk could be contained in the laboratory, why should the wider public have a say? At the same time, the scientists at Asilomar prided themselves on the transparency and openness of their deliberations. Rather than keep their concerns secret, they put them on public display so that society could see and appreciate the scientific community's self-restraint. And like I said, it's become a kind of exemplar of scientific self-regulation. It's referred back to constantly. So Asilomar is remembered as a great success story, as having diffused public anxiety and having opened the way to the benefits of biotechnology. And like I said, it's become a touchstone for the idea of scientific responsibility. Indeed, in convening the 2015 Gene Editing Summit, this is the organizing committee, sorry, from the 1975 meeting. The guy here on the middle of the couch is Sidney Brenner, who died yesterday, I believe. So in convening the 2015 Gene Editing Summit, the National Academies also invoked the 1975 Asilomar meeting as a kind of precedent. Here's David Baltimore again in 2015. In 1975, as today, we believed it was prudent to consider the implications of a remarkable achievement in science, and then as now, we recognized we had a responsibility to include a broad community in our discussions. But this is a false memory. Asilomar was exclusive and narrow in its focus, and it was at the time seen as illegitimate. In 1975, Senator Ted Kennedy voiced a widespread concern when he characterized it as an usurpation of democratic authority. Quote, "They were making public policy and they were making it in private." What ultimately laid public concerns to rest, however, was not a process of engagement and deliberation, but predictions of the future. Declarations by prominent scientists that the biomedical and social, that the public reaction was ungrounded and threatened to inhibit biomedical and social benefits that would flow from biotechnology. The public reaction was, they argued, premature and unwarranted. This was just basic science, and the public ought not meddle with it. Asilomar charted a course for molecular biology that relied heavily on scientific self-regulation and on the notion that scientists are in the best position to make judgments about whether and when a technology warrants public attention. It was underwritten by the notion that technology races ahead of society. Does it sound like a familiar saying? That technology races ahead of society even as it reshapes it. Science acts while society reacts. Once again, from science to technology to society. But if scientific experts are authorized to imagine the future, they are empowered to define the parameters of ethical deliberation, to mark certain scenarios as unrealistic and therefore not worth talking about, and thus to exclude the moral corollaries of those scenarios. Put simply, they get to shut down debate by declaring that it is premature because the technology is just not there yet, and indeed may never be. They get to say that they get to distinguish between what's reasonable and what is hysterical worrying over science fiction scenarios, and therefore must be silenced. The effects of these moves is reflected in tacit commitments to focusing ethical deliberation narrowly on the impacts and consequences of science and technology. The public and its democratic institutions are invited to worry only over the end products of science, not about its processes of judging what forms of research are desirable and good, or about the desirability of the world that that research aspires to or helps to shape. This tends to leave the ambitions that animate such scientific projects uninterrogated, rendering them immune to evaluation, deliberation, and democratic correction. Put simply, the question of whether we're going somewhere that we want to be going is delayed until the technological destination is already in sight with potential associated disasters. That is, quote, when the unthinkable has become conceivable. In this kind of scenario, the only choice we're left with is a highly attenuated one, yes or no, prohibit or acquiesce to an already established technological trajectory. This way of limiting the range of moral imagination has been formative for the relationship between bioscience and bioethics. I want to argue that these patterns are structural. They're fundamentally built into our institutions and the way these projects of deliberation are organized and delimited. Things tend to go like this. Scientific experts tell bioethicists what the future holds. Bioethicists then assess their ethical implications, if any. Instead of asking what norms should guide scientific and technological aspirations, mainstream bioethics tends to focus more narrowly on evaluating specific technologies. Ethics, in effect, becomes a reactive enterprise, subsidiary to a kind of given and advanced science and technology. Let me give just a couple of examples of how this works in practice. So just about every public bioethics body that begins work on a particular issue starts by first calling upon scientific experts to provide the background. In fact, most conferences that you've attended that deal with whatever issue begin with the experts and then move on to the ethicists and et cetera. So then you move on to the ethicists to talk about the implications, and in this structure, ethics is necessarily reactive. It's reactive because it defers to expert accounts of what's possible and thus what warrants ethical attention. We all learn what we need to know first, and then we reflect on its ethical meaning. So it proceeds as though the ethical questions must wait until there's a technological reality in the world for them to attach themselves to. Instead of asking what norms should guide scientific aspirations, it asks merely what norms should guide technological applications. Let me give another example of this in practice. This is a statement made by Arthur Caplan, a very prominent American bioethicist, a few years ago. This was in the context of a discussion of so-called mitochondrial transfer or mitochondrial replacement therapy. This is the three-parent embryo, allowing a woman who has mitochondrial disease to produce a child who theoretically won't by, in effect, taking the cytoplasm from using an egg that's from a third party that includes everything except the nuclear DNA, which comes from the genetic mother. So in this sense, it's a kind of proto-germline genetic engineering because the mitochondrial DNA from the third party are then passed on, if it's a girl that's born, are then passed on to her children and so forth. So it's of nuclear DNA, it's of mitochondrial DNA, not nuclear DNA. So in this statement, Caplan is responding to the suggestion that saying yes to this technique crosses a line and thereby opens the door to other forms of germline genetic engineering. I understand the concern about where we might go. I'm going to worry about that when I get there. Science first, technology second, ethics last. It's notable that when a National Academies committee evaluated mitochondrial replacement, it took Caplan's approach. The committee treated this technique as a circumscribed problem, unrelated to broader considerations of reproductive control and genetic enhancement. Yet only 1 year later, another National Academies committee, that included a certain number of the same members, issued another report, and in that report declared that human genetic engineering was indeed permissible, a radical departure from the long-standing prohibition against it. The second committee leaned, in part, on the reasoning behind the mitochondrial transfer report. So by narrowing the scope of debate and moving incrementally from one technology to the next, worrying about it only when we get there, prior judgments supplied precedents for subsequent ones. This is despite the fact that those prior judgments were supposed to be limited to something very narrow and specific. These one-off judgments not only lay the foundation for the next one-off judgment, they also contribute to the technological, biomedical, and social conditions that encourage scientists to unilaterally race ahead. So when I gave a version of this talk just a few months ago, I pointed to the way much of the sort of talk among leading voices, including the authors of this report, have been about rogue actors, rogue scientists, rogue physicians, and even rogue states. This way of talking sort of had the effect of making out mainstream science as beyond reproach, and implied that the only reasonable ethical worries about human genome editing are about the potential for misuses by marginal rogue actors. When bad things happen, it will be because of bad people misusing a good technology. And true to form, the scientist in China has been labeled a rogue. Yet in the history of reproductive medicine, it's worth remembering that yesterday's rogue is today's paragon of responsibility. So consider this. Robert Edwards and Patrick Steptoe, who produced the first IVF baby in 1978, did so in secret with significant unknowns about the risks and without meaningful professional, let alone public, debate or permission. The highly controversial experiment was revealed through the popular press months before scientific details were published. The advent of numerous other techniques in reproductive medicine has followed a similar pattern, particularly in the 1980s and 90s: cryopreservation, ooplasm transfer, intracytoplasmic sperm injection, to name just a few. That was then. But things really have not changed. Here's a study that was published in late 2015 in PNAS, one of the most prestigious scientific journals in the world. It uses a technique called round spermatid injection, the sort of direct injection of a sperm precursor. Researchers had a hard time making this technique work in mice, and so they tried it in humans. According to the paper, the 14 babies produced in this way have not yet shown any significant health problems. Yet, the authors go on to say, it's probably premature to assume that the technique is safe. Only more time and more babies will tell. Or take this example. A couple of years ago, a New York City-based fertility specialist announced that he had gone to Mexico to perform the mitochondrial transfer technique that I was talking about a few minutes ago. The first baby produced in this way was produced in Mexico, quote, where there are no rules, and he went there, quote, because to save lives is the ethical thing to do. This was, of course, creating a life, not saving a life. And now we have heritable genome editing following the same pattern. This is not an accident. The pattern reproduces itself precisely because it is self-justifying. He Zhonghui, the Chinese scientist who undertook this project, looked directly to the example of Robert Edwards, who went from being seen as a rogue to being seen and remembered and valorized as a pioneer and hero. Indeed, a few years ago, Edwards was awarded science's highest honor, the Nobel. So there's an entrenched pattern of boundary pushing that takes liberties with human lives in the name of notoriety and prestige, and it reproduces itself by producing these as hero stories that the next generation seeks to emulate. So the mitochondrial transfer technique is also exemplary of a related pattern. It was developed in response to what was seen as an urgent medical problem, making it possible for women with mitochondrial disease to have genetically related children. Once it was done, I believe 2 times for that purpose, it was redeployed simply for the purpose of enhancing fertility, for age-related infertility, rejuvenating old eggs. There's now a clinical trial underway in Greece, sponsored by a Spanish company, that is testing it not for mitochondrial disease, but again, for age-related infertility treatment, because that, after all, is where the market is. And this is not a minor intervention into, I mean, this is what the biomedical significance of this is, who knows? the preclinical work involved the production of a couple of rhesus macaques, like 2, okay? So they're now more humans than monkeys. So it's also instructive that the first application of human genome editing was not to correct a disease-causing gene, but to confer an ostensibly desirable trait. It was a kind of enhancement, a genetic vaccination. It was a change of a gene, CCR5, which is a T cell, codes for a T cell receptor, that basically makes you, in effect, makes somebody with this inactivated gene immune to HIV. So American scientists have repudiated this Chinese scientist, He Jiankui, for what they see as a medically unnecessary intervention. That's the criticism. But it's worth noting that in China, HIV/AIDS is profoundly stigmatized, and stigma tends to attach not just to individuals, but to families. The twins' father, the genetically edited twins' father, is HIV positive. So the rationale behind the intervention was that they would be inoculated not just against the disease, but against the stigma associated with it. It would therefore be impossible for them to catch this contagion, biological and social, and everyone would know that. This is, in effect, a genetic fix for a social problem. As such, in my view, if I'm going to engage in a little prediction of the future, I think this is exemplary of the sort of uses heritable genome editing is much more likely to be used for, at least much more widespreadly, than the kinds of uses, the kinds of medical uses it's being contemplated for by experts like the National Academies Committee. And just like mitochondrial transfer is being used for treating infertility, not avoiding mitochondrial disease, this will follow the same pattern, a pattern that points to in a very worrisome direction. I think if you start to think about the kind of social problems that one could imagine genetic interventions for, it's really a parade of extraordinary horribles. And yet, we should appreciate that pattern is of our own making. It's not exceptional or marginal, it's mainstream. It's not rogue, it's normal. And it is so precisely because of the system of research governance that we've put in place, that we put in place and committed ourselves to, asking certain limited questions about the technical possibilities that are already before us, and not about the larger norms that might lead us to pursue those possibilities. Put simply, our approaches to ethical deliberation and research governance have tended to focus narrowly on particular experiments, techniques, and technologies, looking only at the next step, staring at our feet rather than looking ahead to see what trajectories we're walking down. There's a tendency to just assume that the larger trajectories are virtuous. So long as research proceeds apace, it will, one way or another, carry us into a better future, so long as we mitigate the risks and unintended consequences and so forth of the things that we're doing in the moment. I want to point to just how consequential the narrow focus on risk is for this process, a focus that also makes elite experts the arbiters of what should or should not be done. Recall that the prohibition in the US against germline genetic engineering has been grounded in part in a technical judgment that it was too risky, so there's nothing to talk about. Because it was so risky, no one responsible could think it was appropriate to try it. It was, in David Baltimore's words, unthinkable. So no need to engage in ethical deliberation about it, only about the rogues that might violate that norm. Yet the effect was to leave open the question of whether it could ever be acceptable in principle, while simultaneously discouraging deliberation about what positive criteria would have to be met in order to reverse the prohibition. So long as the technology isn't there yet, there's no warrant for questioning it. It's too earlier in the linear sequence. Yet now that the technology has arrived, prominent authorities have declared that the prohibition was in fact never anything more than an expert judgment that it was not possible or that it was too risky. Now that this technical judgment no longer holds, it can be done and it can possibly be done safely, neither does the prohibition. So, an incremental move, thus in a kind of incremental move, the National Academies has made a radical reversal by abandoning the prohibition. It's declared that a long-standing ethical limit is untenable and unreasonable precisely because it's become technologically feasible to transgress it. And that declaration is in turn grounded in the same scientific authority as the prior declaration that it was unthinkable, inconceivable, and therefore needed not be the subject of ethical debate. So a prohibition that may have been grounded partly in technical considerations about safety, but was by no means limited to these considerations, is, in the present controversy, being reframed as reflecting no consensus at all beyond technical judgments about safety. So this is illustrated in a statement made by Richard Hines, a prominent scientist who co-chaired the National Academy's committee that authored this report. Quote, "There has been a line drawn by many that says you should refrain. That was mostly because there was no way of considering how to do that at all, so nobody was arguing that it should be done. Thus, a complete reversal is presented as nothing more than an incremental technological step forward. Note that this becomes a tacit norm. Scenarios that are deemed by scientific experts to be implausible and unthinkable ought not be the focus of deliberation. The corollary is that any ethical prescriptions that are made before a technology exists are subject to revision if and when it's realized. Ethical judgments must be revised in reaction to the current state of technology." This has been said by the way of the Oviedo Convention, which is binding law in 29 European countries, that it sort of doesn't count, that it was made when it didn't mean anything, and so now it should be thrown out or at least revisited. This imposes a kind of hierarchy of justification for ethical limits. Technical evaluations of risk are elevated over other sorts of normative judgments. One important consequence of this is that this creates a kind of imperative for basic research to evaluate and address questions of safety. Once those questions are settled, then you can move on to the other ethical questions. So in much of the discourse emanating from scientific arenas, the notion that the human germline is inviolable has been eclipsed by a kind of discourse of the inviolability of basic research. Indeed, during the 2015 summit, when a scientist stood up to declare that there is no justification for placing any limits whatsoever on basic research, the room erupted into spontaneous applause, one of two moments in the three-day meeting. At a meeting that was grounded in the idea that there is, as Baltimore said, quote, "a responsibility to include a broad community in our discussions," every session ended before all the questions and comments could be heard from the floor. There were lines still at all of the microphones, with one exception, the session on basic research applications, which in effect meant laboratory research involving human gametes and embryos. That session ended 20 minutes early because no one had anything to say. In a meeting that ostensibly represented the interests and concerns of the entire global community, not a single nod was made in that session to the fact that such research is, to put it mildly, a matter of significant ethical disagreement in American public life and in public life in many other places as well. And I think we should not underestimate the implications of human genome editing for this matter of ethical concern. While there's been much talk about editing gametes and embryos to make genetically altered children, the primary and more immediate uses of human embryos is in quote-unquote basic research. Research that's partly justified by the notion that laboratory research is necessary to ensure that should we decide ultimately that clinical applications are okay, we need to make sure that they're safe, and this will do it. CRISPR represents an extraordinary tool for manipulating early embryos in order to understand embryogenesis and for transforming and reconstructing embryos or embryo-like entities for myriad experimental uses. This was an experiment that was done in 2017 by a researcher at Oregon Health and Science University. He created something like 130 embryos specifically to attempt to correct them. By far the largest number of embryos that have been created specifically for research in any published research that I'm aware of in this country, or I think just more broadly. So there are Rubicons are being crossed, significant Rubicons are being crossed that go beyond simply the editing of a couple of children, significant though that is. So CRISPR represents an extraordinary tool for manipulating early embryos in order to understand embryogenesis and for transforming and reconstructing embryos or embryo-like entities for myriad experimental uses. Rapidly advancing techniques of in vitro gametogenesis, producing gametes in vitro from stem cells, are likely to generate a vast new supply of human embryos for experimental research. The experiment that I showed you the picture of just a minute ago They, had to go 3 floors down to the fertility clinic and convince some women to supply eggs, leftover or extra eggs from their fertility treatments. But if you can grow them in vitro, it's much easier and cheaper to get them that way. And new techniques of embryo, cell, and tissue culture are likely to allow the embryo or embryo-like entities to be adapted for a huge range of experimental uses, including at far more advanced developmental stages than has been possible to date. I've been involved in some discussions about this at very sort of high-level universities. One of the sort of top labs in the world who is doing this kind of research, the growing of human parts, partial human organisms through a variety of engineering techniques. And they're very concerned, actually, about what ethically illicit territories they may stray into, and have absolutely no idea how to ask the question. I was involved in a discussion where they brought this to the ethical oversight body, and the ethical oversight body had absolutely no idea how to ask the question, but was convinced that they were the right ones to ask the question of. Of course, no one else knows the nature of those discussions because they happen behind closed doors. They're part of the apparatus of institutional oversight. So it's instructive to look at the ways existing ethical limits are breaking down as science is advancing. For instance, there's been a long-standing rule that human embryos should not be cultured in vitro beyond 14 days of development. Indeed, this is codified law in a number of jurisdictions and is informally adopted in others, including the United States. Until recently, it was only possible to reliably culture human embryos up to 9 days of development. So in a sense, this was a rule that never needed to be applied. But now there are techniques for culturing embryos up to day 14 and beyond. This newfound ability to test the 14-day limit in practice has led immediately to calls to revise it. And let's just pause and appreciate this. It's really a remarkable claim that a rule, no matter what you think of that rule, it's a remarkable idea that a rule, codified as law in many places, requires revision simply because it becomes possible to break it. But it reflects a pattern of ethical standard setting that where ethics follows science rather than the reverse. It becomes possible, becomes thinkable, it becomes conceivable, and therefore we have to ask the question anew, what should we do? Again, genome editing is following the same pattern. The news of the Chinese babies broke on the eve of the second international summit, which was held in Hong Kong last November. That news elicited swift condemnation from the summit organizers, and in my view, rightly so. But barely a day into the summit, one of its leaders, the dean of Harvard Medical School, was already calling for picking up where the Chinese rogue had left off, doing responsibly what He Jiankui had done irresponsibly. He said, simply because the first step was a misstep doesn't mean that we shouldn't pause and reevaluate and move forward. Move forward. The direction was set by a rogue, and we follow along the same pathway. So to conclude, I've been describing the moves that are commonly made to narrow and circumscribe ethical debate to the impacts and consequences of new technologies upon society, thereby preserving the authority and the autonomy of quote-unquote basic research. But the projects and aspirations that animate that science will necessarily shape and come to be embedded in the technologies that it gives rise to and the way they come to figure in our world and in our lives. This is so not least because the ethical norms that orient that research reflect underlying ideas about the ways, about the forms of human life that warrant protection and what can be made an object of instrumental control. The issues I've been discussing, I want to point out, are problems of democratic governance. At stake is not just how the technology gets governed, but what ways of governing we commit ourselves to, and what we makes those commitments. If we look past the technologies of the moment to take these allocations of authority and responsibility as objects of reflection in themselves, the patterns as opposed to the objects of concern in the moment, we start to see the importance of the question of who gets to imagine the future. And we see that that answer fundamentally shapes how we end up governing science and technology, the who. At stake in it is not only the question of what futures are possible, but in what ways we're going to imagine those futures, in what terms, how narrowly or broadly, how inclusively or exclusively of alternative and dissenting imaginations, drawing upon what moral repertoires. Governance, in my view, is actually an apt word for this. It's a nautical term. It originally meant to steer the ship. If we think of governance as steering, we need to ask what trajectory we're on, towards what future, who's at the helm, and navigating with what instruments. To borrow a nice phrase from the previous talk, we need to ask, are we on a ship without a compass? The history of biotechnology is littered with things that didn't come to pass quite as we imagined them. But what we find ourselves with at the end of the day, regardless of whether a given technology comes into being, are new forms of institutional capacity, altered practices of deliberation and governance, and shifted repertoires of moral imagination. We're remaking our institutions of governance in a sense more profoundly than we're remaking our technological repertoires. The technologies I've been discussing are likely to be incredibly consequential for human lives, and thus also for our shared moral and political conceptions of human dignity, identity, and integrity. And really fundamentally for the authoring of human futures, molecular and moral. Here, once again, is the statement that I read before from Oppenheimer. And here's a statement that he made less than a decade later, explaining how that sin was committed. When you see something that is technically sweet, you go ahead and do it, and you argue about what to do about it only after you have your technical success. These notions of sinfulness and sweetness are both affirmations of the world-altering power of science. At stake in the governance of science and technology are our deepest commitments to notions of human integrity and dignity, to ideas of the kind of lives that we want to live, the kind of societies we want to build, and how those ways of life should be preserved or protected. It's a power that should and must answer to a we that is larger than itself, even and perhaps especially when that wider we sees good reason for setting limits on science in the name of a greater good. 60 years ago last year, the philosopher Hannah Arendt presciently worried that if we channel our human creativity into technologies like human genetic engineering, she was already talking about this 60 years ago, we may find ourselves, quote, unable to understand, that is, to think and to speak about the things which we are nevertheless able to do. Understanding, she noted, is a matter of politics in the best sense, of becoming a we that can think and speak together in ways that orient our lives and societies to the good. It was an ambitious hope to seek such a politics in that broken moment when the ovens of Auschwitz had not long been cold, Sputnik had just soared into the heavens, and the bomb, that extraordinary product of scientific genius, threatened to extinguish civilization itself. Ours, too, is a moment that demands such radical hope. It demands that we resist the temptation to draw down morally challenging problems into narrow processes of setting scientific standards. It demands that we take up the hard and virtuous work of thinking and speaking as a human community, of gathering ourselves together and imagining the technological futures we wish to welcome or to shun. Yet if we simply push forward, thoughtlessly perfecting the technologies that lie before us, come what may, little good and much harm will come from these powerful things which we do not understand but are nevertheless able to do. Thanks.